Hello, my name is Michael Wolf. I must confess that I raised my arm when Sivak asked who is a mathematician, although I hesitated. And in the next 30 minutes, I'm going to tell you a story about how our insight into why the circle cannot be squared can, at least occasionally, also give us insights about certain aspects of quantum systems, quantum information, and quantum computation. But before going to the quantum world, let me go back to squares and circles, in case I manage. I don't. Okay, let's do it like this. And let me, no, it's not working. Is this the right one? Or maybe is this the right one? Yes. Okay, sorry. And let me go back 2,500 years to the Greek philosopher Anaxagoras. He was back then sitting, in fact, he was sitting in prison, like most of the ancient Greek philosophers, apparently, but at some point sitting in prison. And he was sitting there because of his lack of respect for the divine nature of the sun, because he claimed that the sun is just a big fireball. And there he used his time and thought about the problem of squaring the circle. And he's the first person we know of who thought about this problem. So let's remind ourselves what this problem is about. So the task is given. I will find out until the end of the talk how to use this. Given a ruler and a compass, construct in a finite number of steps a square with the same area as a given circle. And Anaxagoras did not find a solution to this problem. In fact, it was an open problem for roughly 2,500 years until Ferdinand von Lindemann, who was in his later days professor at the LMU in Munich. So 140 years later, he would have been member of MCQST, of course. He showed that this is not possible, which did not prevent other people from finding solutions to the problem. And one very nice and very hilarious paper that was published on this is by Edward Goodwin. But maybe let me put this aside in case in the end there's time for questions. Nobody wants to ask a question and you want to break the awkward silence and ask me about the history of this publication. So what did Lindemann do? So Lindemann showed that this is impossible by showing that pi is a very special number. If we look at the real number line, then we know that there's this hierarchy of different levels of abstraction. So there are the integers and there are the rational numbers that Pythagoras loved, and then there are these roots of polynomials with integer coefficients that Pythagoras didn't love so much. And then in the 19th century, people found out that this is not everything. There are other numbers. So there are other numbers than these algebraic numbers that we now call transcendental numbers. And Lindemann showed that pi is one of those transcendental numbers. And why does this solve this can you square the circle problem? Well, it solves it because whatever you can construct with a finite number of steps with ruler and compass follows algebraic rules. So you can describe this using polynomials. And you will never ever enter this blue regime and get something transcendental. Pi, however, is transcendental. Okay, so this solves this problem. We know other numbers that are transcendental. However, proving that a number is transcendental turns out to be a very subtle and tricky business. Yeah, so there are some clean cases like e and pi and the logarithm of integers larger than 1, of natural numbers larger than 1. But as soon as you deviate slightly from these clean cases, proving that a number is transcendental becomes very quickly out of reach. Yeah, so for instance, we don't know whether e plus pi, e times pi, or pi to the power square 2, whether these are transcendental numbers. Most likely there are, but proving is a different question. So this concept or this separation, algebraic versus transcendental, this does not only exist for numbers, it also exists for functions and for sets. And a function is called algebraic if its graph is, at least locally, the solution to some polynomial equation. And again, there are the usual suspects of functions that turn out to be not algebraic, the exponential function and the logarithm. Then concerning sets, sets is called, so if you regard a set as a subset of some real vector space, then this is called semi-algebraic if it can be described by a finite number of polynomial inequalities. Yeah, and then the semi in semi-algebraic refers to the fact that we allow ourselves to also use inequalities and not only equalities. Okay, so what does this have to do with information theory and with quantum theory? So this separation between algebraic on the one side and transcendental on the other side often comes hand in hand with a distinction between single shots. I'm very sorry. I'm no longer so sure that I will learn this until the end of the talk. Between single shot theory and asymptotic theory, between finite resources, infinite resources, between finite systems and the thermodynamic limit. And now I want to give you 3 examples, one old known one and 2 new ones, where you see this distinction working hand in hand with the separation between algebraic and transcendental. And the first one is a well-known one, which I learned from one of Bruno's papers, the old 92 paper where he, with Fannes and Werner, introduced finitely correlate states, or AKA matrix product states. And one of the many observations in this paper was the following. So if you look at a quantum spin chain with n spin 1/2 particles, and these spins, they interact governed by an antiferromagnetic Heisenberg Hamiltonian, and then you ask yourself, what's the ground state energy per spin? And for any finite number of spins, since everything in the problem description is algebraic, this ground state energy is also algebraic. Yeah, so for any finite system size, you end up with an algebraic number. But in the thermodynamic limit, you end up with a transcendental number, with a transcendental ground state energy per spin. The same setup also gives a nice example for semi-algebraic versus transcendental sets, because if you now look at the set of all 2 qubits density operators that can arise as reduced state of an infinite spin chain, then basically for the same reason as above, it turns out that that this subset is not a semi-algebraic set, so let me call this a transcendental subset. Okay, but if you ask the same question for a finite system, it will turn out to be algebraic. Okay, so now let me show you 2 new stories where this separation appears and can be applied. One is in the context of catalytic state transformations. So this is something that was discussed in depth by Wilming and co-authors. And there the question is the following. So assume you are given a density operator rho and you ask yourself, is it possible to transform rho into a target state rho prime under the following rules? So you're allowed to add an ancillar state, sigma, to perform a global unitary on the combined system. And then the requirement is that the final state, which might be correlated, is such that on one subsystem, you obtain the target state, at least to a good approximation. And on the other subsystem, you recover the ancillar state. So the ancillar serves as a catalyst. Now the question is, when is this possible? So given rho, what is the set of states rho prime that is reachable in such a scenario? Well, now we can define the set of density operators that is reachable starting from rho. So this is Cn. So Cn is the set of density operators reachable if you impose that the dimension of the catalyst is at most n. This is some subset of the set of density operators. Let me introduce another subset, namely the set of density operators whose von Neumann entropy is larger than the von Neumann entropy of the initial state. Remarkable results by Wilming, or remarkable observation by Wilming and co-authors, is that if we take the union over all these sets, so if you do not impose a constraint on the size of the catalyst, then these two sets become equal. So in some sense, the limit of the set of reachable states becomes the set of states whose entropy is larger than the one of the initial state. And this immediately poses the question, or raises the question, whether one really needs this limit. So if the initial state has a certain dimension, like 3, is it really necessary to have a catalyst that has infinite dimensions? Or could it be that catalysts of finite dimension also do the job? Maybe the catalyst dimension is some function of the system dimension, like system dimension squared or something like this. Okay. So now let me try to argue that this is not the case, and let me do this the Lindemann way, the you shall not square the circle way. And this is done in the following way. So the first observation is that this set for a finite n, finite ancillar dimension, is a semi-algebraic set. This is due to the fact that, well, everything that appears is algebraic, and then there are these quantifiers, but then there's the very powerful general theorem by Tarski and Seigenberg that tell us these quantifiers don't matter, it's still semi-algebraic. Okay. Now this set, however, where we constrain the entropy, this smells very transcendental, right? Because there's the logarithm involved in the definition of the entropy. So if we would be able to show that this is a transcendental set, then it's clear that there cannot be an equality between the two sets for a finite dimension of the catalyst, right? Because one set is algebraic and the other set is transcendental. Okay, so is the set transcendental? Well, it depends on the dimension. So if the dimension is 2, then it's rather obviously not transcendental. It's very, very, very algebraic. Because the qubit states, so the density operators on a two-dimensional Hilbert space with a fixed entropy, they can also be characterized, for instance, by the purity. Yeah, and we know that in the Bloch representation, the set of density operators with a fixed entropy is just a sphere. Yeah, so it doesn't matter that a logarithm appears in the definition of the sphere. The sphere is super algebraic. Okay, which is not a technical term; it's algebraic. Okay, so what about for dimensions larger than 2? There it turns out that the set is nowhere semi-algebraic. So in a sense, it's everywhere transcendental. Let me sketch by picture the idea for proving this. So suppose this blue convex set is the set of density operators with a given entropy. Now, so this is a manifold, and now we can assign a normal vector to every point on this manifold, and we can assume that this normal vector, which is perpendicular on the tangent space at this point, this normal vector has unit norm. So in this way, we can assign a unit vector to every point on this manifold. And this assignment, this map, is in some parts of mathematics, it's sometimes called the Gauss map. Okay. Now let's look at a path in our manifold that goes through the state that we consider. Now this path, and we construct the path by intersecting with an algebraic surface. Now this path is also mapped to a path on the unit sphere by this Gauss map. And now we can pick out one of the components, let's say the x components of this unit vectors, and then by looking at the x component or by any other component which is not constant on this path, we obtain a function or a snippet of a function from R to R, namely from the parameter that parameterizes this path to the components of this unit vector. Okay, and this snippet of a function from R to R we can put into the complex plane, and then we can say analytic continuation. So let's say analytic continuation. Okay, and then something happens. Nobody knows what happens exactly, but what happens exactly is not so important. What is important is, and this is maybe something that you recall from your complex analysis class, when you look at a logarithm and do the analytic continuation, then you get this infinite number of branches popping up. If you do the same with an algebraic function, like with a square root or cubit root, you also get several branches, but only finitely many. Okay. And this infinite number of branches that you obtain, or more technically speaking, the appearance of a non-compact Riemann surface, is exactly what or how the logarithm that appears in the definition of the set reveals the let's say the transcendental property of the sets, right? Okay, I don't know whether all this makes sense, but it's a nice picture, and this is the basic idea behind the proof. Okay, so what we can show is that if the dimension is larger than or equal to 3, and the entropy values is not extremal, so the entropy is not 0 and it's not maximal, then this entropy constraint set is noble semi-algebraic. It's everywhere transcendental, and the same is true. The theorem and also the proof idea extends to other entropic quantities like the relative entropy, and also extends to cases where we impose an additional constraints, like we put an additional energy constraints in addition to the entropy constraint, and the same result holds. Okay, so this means somehow from a distance that there's no algebraic single-shot characterization of these quantities, unless there's an ancilla, like our catalyst before, involved whose dimension is unbounded. Okay. Oh, how much time do I have? Okay. Okay. A short second story. A very different story, but in the words of Sivak, same punchline. About circuit complexity. So in 1948, the father of information theory, Shannon, realized that almost all Boolean functions require Boolean circuits of exponential size. And then it's a simple counting argument. So if you have a function from n bits to a single bit, and then you count the number of functions, you count the number of circuits, Boolean circuits, and then you realize, well, most of them, and one can quantify this, need a circuit of exponential size. This becomes interesting if you realize that despite the fact that we know that almost all functions have exponential circuit complexity, until today there's no explicit example, not a single one, where the circuit complexity is more than linear. Yeah? In fact, even 4n is not provable. Yeah, I think the best explicit example is 3n plus something. I find this hard to believe, but computer scientists tell this is the case. And it's also the case in the quantum context. Yeah, so in the quantum context, if you take your favorite book, Nielsen and Chuang, open it on page 198, and then you can learn that almost all n-qubit unitaries and states need exponential circuit size. So can we? Okay, and in a similar way as in the classical context, explicit examples with superlinear circuit complexity are elusive. Okay, so now what I want to do in the remaining 2 minutes, maybe? Still 5? Nobody knows. Okay, I will just continue. To use the Lindemann "you shall not square the circle" strategy in order to come up with explicit examples of exponential circuit complexity. Okay, and this follows the following very, very simple idea. So if you look at this circuit and at the matrix entries of all the, let's say, 2-qubit gates that appear there, well, of course, these 2-qubit gates, they can have transcendental numbers as matrix entries. Yeah, so it's not that things are algebraic to start with. They may not be algebraic. However, if the circuit is of polynomial size, well, then there are only polynomially many different transcendental numbers that can pop up. Okay. Now, the final state or the final unitary that we obtain from the circuit, of course, is such that the individual matrix entries of those gates, they do not pop up directly, but they are somehow processed. But they are processed in an algebraic way, right? Because we take tensor products and we take products. All these are algebraic operations. And these algebraic operations, they cannot increase the number of algebraically independent transcendental numbers. Okay, so if we count the number of algebraically independent transcendental numbers, okay, and this is called the transcendence degree, then this gives us a lower bound to the circuit complexity. Okay, and then there's this factor 16 in between, but 16 is just the number of matrix entries of an individual 2-qubit gate. Okay, so now we have a circuit complexity lower bound. Now we can open the toolbox of transcendental number theory, and then we find very nice toys and tools in this box, and putting them together in the right way. We can cook up examples of exponential circuit complexity. So, okay, maybe I don't go through those in detail. What we can do is we can construct, for instance, diagonal unitaries or maximally coherent states. So this means that all the amplitudes and computational product bases have the same modulus but different phases. And if we choose those phases in this way, where P1 to Pn are the first prime numbers, then we take square roots, we take suitable products of those numbers, and we put them together in this way, then one can show that the unitaries constructed in this way and the states constructed in this way have circuit complexity that is at least 2 to the n-4. So this could be called exponential. The proof has 2 ingredients. One is an old work of Bizikovic, who produces large sets of algebraic numbers that are linearly independent over Q. Okay, why should we care? Because we want to have something transcendental. Well, but then we can use this result and lift this up using the Lindemann-Weierstrass theorem, because this somehow elevates what is algebraic here to transcendental, and what is linear independent here to algebraically independent. Okay, so in this way one can show that these sets of numbers are sets of large or of exponentially large transcendence degree. Okay, so now one possible complaint, and one I would have immediately, is that this is about the exact generation of the states and unitaries. But maybe we can approximate these states and unitaries efficiently. I would say, okay, being optimistic today, I would say this is work in progress. What I can say is concerning approximations is the following. So there's this additional parameter, integer parameter t up here, and the argument works for all t's. So now let's not look at a single unitary or at a single state, but let's look at a large family of unitaries or states with exponential exact circuit complexity. And then what we can show is that within this family, all but a doubly exponentially small subset is such that these unitaries or states, they can also not be efficiently approximated with constant error. Yeah, so in other words, for most of these examples, the property of having exponential circuit complexity is stable under basically arbitrary perturbations. Okay. So now some of you may still wonder what this guy wanting to tell me. So let me start all over again and try to give you a takeaway message. So what I wanted to tell you is that this distinction that is often made between single shot and asymptotic theory, or between finite and infinite resources, or between finite systems and thermodynamic limit, very often goes hand in hand with a separation between algebraic on the one side, or semi-algebraic concerning sets, and transcendental on the other side. And that in many cases, or at least in some cases, we can use this separation to prove no-go results, like you cannot square the circle, or you cannot find certain single-shot characterizations of information-theoretic quantities, or you cannot find an efficient representation of certain high-complexity tensors. Okay, I know this was all very vague, but I know two persons in the room who can ask, who you can ask, and who are able and probably happy and willing to answer all your questions. And these are the people who did these works. So this Vjosa Blakhaj, who wrote the paper on transcendental properties of entropy-constrained sets, and Yi van Jia, who wrote a paper with the beautiful title, Hay from the Haystack, Explicit Examples of Exponential Quantum Circuit Complexity. They're both here, and they both have posters. Thank you.
So thank you very much for this really interesting talk. Does anyone here have any questions, or also online? I mean, don't be shy. You were giving the question at the beginning. So, oops, sorry.
I would be just interested in this. Thank you for the very nice talk. I would be just interested in this publication from 1894, which you showed in the introduction.
How comes? So in fact, this was the basis of what is called the Indiana Pi Bill, and you may have heard about this. Yeah, so this Edward Goodwin, who published this, he published this in American Mathematical Monthly, which is in principle a serious math journal. And then you might wonder, how can this happen? But then if you look at the fine prints, and then you see that published by request of the author, which in my translation means that the author paid for the publication, and therefore all scientific standards were waived. And then this publication made it to the House of Representatives in the state of Indiana, and it's not so clear. So I tried to find out, but I couldn't, because the paper is not clear what this bill, the Pi Bill of Indiana, was supposed to do. Some people say it was supposed to be to set pi equal to 3.2. But if you read the first two sentences, or even just the first one of this, then you can understand that pi is in fact equal to 4. So it's not clear to me what this is supposed to do. And this, the bill passed the House of Representatives. Yeah, so at first they said, this is not our business, and they passed this on to the Education Committee, but then it came back with some thumbs up, and they passed this with, I think, 67-0. But fortunately, Indiana has these two chambers. There's also the Senate, and there was some mathematician who became aware of this bullshit. And then it didn't pass the Senate. Yeah, so therefore pi is still 3 point something odds and not equal to 4 in Indiana.
Thank you.